So today for the TAP Colloquium, we have Nicole Lloyd who will be speaking about gamma ray bursts. She got her Bachelor of Arts in Physics from Cornell and then went on to get a PhD from Stanford, and then has now a joint appointment between LANL and the University of New Mexico. So we get to learn about gamma ray bursts both from the inside and out. So thank you very much.
Thank you very much. And thank you all for coming to my talk and just for having me here. I think I told a couple of you last time I was in Tucson, I was an undergrad at a AAS meeting here, so that was a long, long time ago, and it's really nice to be back and see all the new faces here. So yeah, gamma ray bursts, inside and out. What do I mean by that? So the focus of my talk today is really going to be what are the progenitor systems of gamma ray bursts. There are probably many. How do we distinguish between them? And most importantly, and what I care the most about, is how do we understand these systems in the context of the history of our universe, of the evolution of our universe. So after a brief introduction, I'd like to focus in on the inner engine and talk a little bit about the black hole disk system that launches the gamma ray burst jet. Then I'd like to discuss some interesting things about GRB environments, some things that we're learning from their radio afterglows in particular that might suggest different progenitor systems. And finally, I'd like to end with a discussion of the evolution of some of their observed properties and how we can understand this in the context of different progenitors. Okay, so I know you all probably know what gamma ray bursts are, but I work at Los Alamos and I'm required by law to tell you their story of how they were just kidding. But so yeah, the first gamma ray burst was detected in 1967, and it was a result of the nuclear test ban treaty between the United States and USSR, agreeing not to test nuclear bombs on Earth, on the moon, in space. But we didn't trust each other, so Los Alamos built the Vela satellites to spy on Russia and to look for gamma ray signatures from nuclear bombs. And they did not see that. Instead, they saw this, so counts per second versus time in around the 200 keV range. So a burst of gamma rays coming from outer space, not from the sun, not from the moon, not from Earth, but from somewhere in outer space, not super well localized. Lasting about 10 seconds or so. I'd like to point out, I said that the first gamma ray burst was detected in 1967, but this publication was 73. And for the longest time, I held the idea that this is because it was at Los Alamos and the information was classified. I recently found out, in fact, that it just took them that long to write their papers. So grad students, it happens to all of us, know that, okay? This is an obnoxious slide, don't read it, but this just shows you, because we did not know the distance to these gamma ray bursts. We didn't know how much energy they were emitting. And so it was an open game of what kind of models can you make to create a burst of gamma rays, and all kinds of things can do it. Relativistic dust grains, chunks of antimatter, nuclear goblins, I'm not sure what that is. White holes are always fun. And primordial black hole explosions are a few things that stood out. There are many, many more. This was just a few that caught my eye. It kind of reminds me of how it was with fast radio bursts a few years ago, before we kind of got a clue of what they are. There were a few alien models of fast radio bursts, if you recall. What's that? Yes?
How quickly was it determined that they weren't on Earth?
Pretty right away. Like, there was localization good enough to know that they were coming not from Earth. Yeah, pretty instantly. Yeah. So satellites got better, and a lot more data came in to study these specifically. So the BATSI satellite in particular helped us learn a lot. And here's a few things I'd like you to keep in mind as we go forward in this talk from the data side to help us understand what these things are. And one of this is 12 different gamma ray bursts coming from 12 different spots in the sky. We've never seen one repeat. They again, counts per second in around the 250 keV range. And you'll notice they have rapid variability, less than a second. The spectrum appears non-thermal in the gamma ray range, mostly. If you've been up how long the gamma ray emission lasts, They seem to clump into two classes, less than about a second and more than about a second. And to me, most importantly, was we learned from this BATSI satellite that they were distributed isotropically across the sky as extragalactic objects are. And so, of course, in '97, when the Bepo-SAC satellite was launched, that had the ability to localize these things well enough such that other telescopes of other wavelengths could follow up, they did so and discovered this so-called afterglow, this long timescale fading across the electromagnetic spectrum. This is not the one from '97. This is just a beautiful example from 2013 of an afterglow. So the idea is you have the gamma ray bursts, and then you have this fading from hours, days, weeks, months, even years across the electromagnetic spectrum. And in particular, the optical information, afterglow, can provide spectral lines to give us a distance to these things, and it did so. So we could localize it and determine its host galaxy, and we could sometimes you can get spectral lines from the host galaxy. And something that was noticed pretty early on is the hosts of these gamma ray bursts tend to be on average lower mass and lower metallicity. But keep in mind, and we'll come back to this, thank you for those of you who've seen Fight Club and know what the heck that reference is all about. Anyway, there's exceptions to everything I'm going to say here. Anything that I say, oh, GRBs do this or that, there's always an exception, including this metallicity requirement and mass requirement for the host galaxies. Okay, so now we know their distance. So we can get an estimate of their energy. They emit around 10 to the 52 ergs. On time scale, within around 10 seconds or so. If you combine just these two pieces of information alone, you can constrain progenitor models. Combined with the variability, which puts a size constraint on your system. So we think, and it has been confirmed at least for some gamma ray bursts, that the short ones are due to the merger of two compact objects, like two neutron stars, for example. Whereas the long ones, if you just take the free fall time of a very massive star, you get the time scale you need and the energetics you need. We believe the long GRBs.
Can you run this again, the simulation?
Which one? Oops, sorry. You both?
Mm-hmm.
Sure. Are you not sick of this movie? Are you all? I mean, I've seen this movie like 8,000 times.
10 seconds and I didn't see it.
Okay, so here we go. This is not, timed accurately. If you time with a clock, I'm not going to get that right. This is like sped up.
So what's the difference?
Okay. What's the difference between these two and the time scales? I'm talking a massive star collapse and the amount of material you have available and the accretion rate that you have in that case will give you time scales of that central engine being active on the order of 10 seconds.
There are distinct peaks, so there must be a...
Yes.
And no one will tell me that the masses in the universe are quantized, so...
No, this is these gamma ray bursts are so-called long gamma ray bursts, and we believe they're associated with the collapse of a massive star. These gamma ray bursts are so-called short gamma ray bursts, and we believe they're associated with the merger of two compact objects. Okay? However...
The time axis is low scale. So it's actually, the spread is pretty,
Yeah. So, but I think, you bring up a point that each one of those cataclysmic events lead to a similar outcome in that you're left with some central compact object, which is likely a black hole, a disk around it, and we think all of this is highly rotating and launching then a relativistic jet.
Can I just follow up with that
Yes,
question?
please.
So if the physics doesn't separate out 1 second and 10, 50, or 100 seconds into two separate things, how is it that you think that one is produced by the...
Why do you say the physics doesn't separate that out?
Well, I'm just trying to get it, I didn't...
So if you just take the amount of mass you have available divided by an accretion rate in those systems, okay, so a double neutron star system versus a massive star, there's a different amount of mass available in each one by a factor of 10, let's say. And your accretion rate, you can make that the same between the two if you want. but in this black hole disk system, this gives you a time scale, right? Mass divided by the accretion will give you this time scale. It's really maybe a matter of how much material you have available in a double neutron star system versus a massive star. That might be the best zeroth order way to understand that distinction there. Is that okay? Does that make sense?
Yeah, I was also hoping maybe for some other. Well, anyways, yeah.
All right. Well, so ask me at the end. We're going to get into some of this stuff, and then if it didn't get at what you were hoping for, ask me again. Okay. All right. Okay. So let me. Yes, please.
For the collapse of a massive star case, why do you expect rapid rotation?
That's a great question. It's not necessary. You need it. You need it to make these things work. You need to launch a jet. In the way that I think that jets are launched, you have to have high angular momentum systems, and we'll get into a little bit of that too. So this is our my cartoon. Well, not mine. Somebody else made this picture, but this is the cartoon picture we have of our understanding of gamma ray bursts right now. Whereas, again, to summarize what I went over, we think these less than 1 second gamma ray bursts are the merger of two neutron stars. 10-second-ish gamma ray bursts are associated with the collapse of a massive star. Both lead to a black hole disk system launching relativistic outflow, variable relativistic outflow, some sort of internal dissipation like shocks or maybe magnetic reconnection causes that burst of gamma rays. Okay, so this here is a reflection of the lifetime of that inner engine. But meanwhile, all of this stuff that's been launched kind of merges all together into a blast wave front, which sweeps up your external medium, and eventually it sweeps up enough to begin to decelerate, and that gives you that long-lived afterglow. Okay, and in this jet, it's perfectly possible to make cosmic rays and neutrinos and cosmic rays in this jet. We haven't seen any evidence of it yet. That's a hard game to play, but it's theoretically possible to accelerate particles to very high energies. We know that double neutron star mergers create gravitational waves, and we've seen one or maybe more. Collapse of massive star will also create gravitational waves if it's asymmetric in any way. That's going to be a very weak signal, so I'm not going to make any claims about being able to see that. But these are truly multi-messenger events and all messages that we usually talk about when we say that term. Okay, so this is our overall picture. So seems like we have a handle, but I will remind you that to everything that I said, absolutely every part of that, there's an exception, or you can validly challenge it in some way and say, but this event did that and not this, and blah, blah, blah. So keep that in mind as we go on. What we're going to do, though, is try to focus on different parts of that cartoon picture and see what we can learn. Yes, please.
So one of the exceptions, at least in the short gamma ray bursts, are the ones with extended X-ray emission.
Yes.
Has that been ever observed for the long gamma ray bursts or something similar?
Yeah, I mean, there's definitely very late time X-ray emission in some. We get like X-ray flares at very late times, later than what we might expect the central engine to be active for. It's an open question. There's a debate about whether or not that is still a long-lived central engine, or there's something external going on, some kind of external process. It's I would say that's open. Yeah, but you do see it in long as well. Any other thoughts on the kind of general overview of GRBs before I move on? Okay, so let's go into the jet launch itself. And so you may know that back in '77, Roger Blandford and Roman ZNAJEK proposed a really nice way to launch jets from a spinning black hole, as long as it has some magnetic flux around it. And the idea is, if you're extracting the rotational energy of the black hole, and what's happening is that because the black hole is spinning, you get frame dragging effects that serve to wind up the magnetic field around the black hole. And this launches a pointing flux along the spin axis of the black hole. So that extracts away the rotational energy of the black hole, but you get a powerful pointing flux along that spin axis. This launches your jet. okay? Simulations already from 2015, maybe even earlier, were showing this, this BLANDFORD-ZNAJEK jet being launched. More recently, and I know Vasilis has worked a lot on this, this is a picture from Ruiz et al. 2019 of two neutron star mergers. Neutron stars with magnetic fields going through this whole BLANDFORD-ZNAJEK process and launching a jet. So you can write it down on paper. Simulations seem to be showing it. What's sort of cool about it to me is that the power that you get from this process, which is kind of ugly and messy, or at least it is to me when I look at the papers, but you can distill it down to something pretty simple, which is a bunch of constants, the spin energy, or the spin parameter of the black hole, the magnetic flux around the black hole, and the black hole mass, or the things that are coming into play here, okay? So this is the power in this BLANDFORD-ZNAJEK jet. So we did something very basic. We said, okay, well, let's assume that the luminosity that we're getting in these gamma rays from this internal dissipation is some fraction of the BLANDFORD-ZNAJEK luminosity. And I picked, 10%. We can fight about that later. It could be lower, surely, probably is. Maybe it can be higher, but it's some fraction of that jet power. Okay. We picked a spin parameter of 0.9. This is also something we can fight about. How do we get highly spinning black holes? I have a comment on that in a moment. But anyway, this is the assumptions that we made, okay? And actually, let me make a comment on the spin. Although I know the black hole, the LIGO spin estimates seem to fall on the low end of things. A lot of the black hole spin measurements from X-ray binaries and AGN are actually pretty high. They do fall up in this range above 0.6 that the simulations seem to be implying we need to launch a jet. So we do think we see highly spinning black holes out there, so I don't think it's such a crazy assumption. But anyway, what I wanted to do is, with that assumption of the efficiency and the spin, what does that imply then for the magnetic fields, or the magnetic flux and masses of black holes that we need to see these GRBs, if this mechanism is correct? So what do I have here? I have magnetic field on the y-axis and black hole mass on the x-axis, and these low black hole masses don't really apply. I have gamma ray burst luminosities, the actual beaming corrected jet observed gamma ray luminosity from the jet, going from around 5 times 10 to the 48 to almost 10 to the 52 ergs. And you'll see for black hole masses around 10 solar masses or so, your fields are like 10 to the 15 Gauss or so. The fields, that's the field at the horizon. So very, very high. Okay.
How are these tracks created? What are you keeping constant?
So
is it the total energy output that is constant? I'm sorry.
Yeah, so that's right. It's the luminosity.
Okay.
It's the luminosity of the jet. Or we're taking the observed luminosity. Okay.
Nobody has any worry that 10 to 12 Tesla is a little bit beyond our...
Sure, yeah, we have worries. That's a big, yeah, of course. I mean, these are really high magnetic fields, and it's something that we'd love to understand. Is that, is that realistic? Is that viable? But let's for a moment imagine that we are getting this type of field strength near the black hole horizon, and let's play that out a little bit.
Well,
I mean, in pulsars, we do see 10 to the 15 Gauss from spin down, and from spectral indications that they possess surface fields of 10 to the 15 Gauss.
Exactly.
In the proto-forming system, the collapsing star with differential rotation, etc., I don't think it's crazy to think that it would be above that.
Yeah, simulations definitely show that you start with a weak magnetic field, you amplify through hydromagnetic instabilities to 10 to 15, 10 to 16 Gauss.
The same thing that gets you your rotation also gives you your magnetic field.
Yeah. Yes, exactly. So, magnetars have saved us from the arguments where people feel uncomfortable with those high magnetic fields, because we do see them, and that's nice. But what does that imply for what's going on around the black hole in your accretion disk? If what happens is your magnetic flux or your magnetic field is so high that the pressure from the field can exceed the ram pressure of the accretion. Okay, So in this case, you get the so-called magnetically arrested disk, where your accretion is stalled from the magnetic flux pressure, the magnetic field pressure. And you get to a point where you can get an interchange instability, where it's sort of a magnetic analogy to a Rayleigh-Taylor instability, where the field and fluid kind of flip, and the field diffuses out into the disk, and then you get the process over again, okay, as the field's advected back in. But what we did, so let's go back to this variability of gamma ray bursts. Remember, it was around 1 second. Again, we looked at this MAD disk in a very simple way. We looked at really just a free fall time in a MAD disk. And we found this plot I'm about to put up. I made it, but I don't love it. This is this MAD time scale. So again, the free fall time in a magnetically arrested disk in a GRB context versus the radius to which the disk is arrested. And this is just showing, these lines are just showing a bunch of different black hole masses and kind of degrees of arrestedness, which is parameterized by this little epsilon here. It's a way to say how arrested is your accretion, and it's a way to parameterize our ignorance, much in the way sort of you do with an alpha disk. But the point of this is that these vertical black lines are encapsulating the observed variability timescales of gamma ray bursts, the flickering timescales. And they, a range of MAD models, MAD disks, fall in a GRB context, fall into this variability timescale. So it is a natural way to explain that variability. And I'll remind you that gamma ray burst variability is a reflection of that central engine variability. But what's, I think, even kind of cooler is that, let's focus on the blue dots here, is the variability time scale in a gamma ray burst, and the x-axis is the Lorentz factor of the jet, the kind of average or overall Lorentz factor of that relativistic outflow. And there's a strong anti-correlation observed between that. How variable is your gamma ray burst, and how high is that Lorentz factor of your jet that you get, say, from your afterglow measurements, okay? And that falls out very naturally if you plot that MAD time scale versus the maximum Lorentz factor you'd expect in a BLANDFORD-ZNAJEK framework. That correlation falls out naturally in that context. I think that's all I'll say for this for now, because I want to talk about other things. If you have questions about this, I can go over the equations with you and show you how it does so. But the point of all of this is that these MAD disks, which seem to be necessary if we believe that BLANDFORD-ZNAJEK is the mechanism of jet launch, actually fall in line with a lot of the observations that we see in GRBs. Yes?
2 questions.
Yes.
One, this assumes that you have that constant epsilon constant. It applies the same universal epsilon for all GRBs?
So, yes. No, yeah, I picked, constant epsilon, that's correct, yes.
Okay. And the other is, how does the BZ effect explain the maximum Lorentz factor?
So that part comes really from, the assumption here was an INDAF disk launching a wind. It was launching a wind into your jet region, and that maximum Lorentz factor mu has to do with the amount of baryon loading that you get then from that wind from your disk. Okay, but you determine it by the power also that's given to your jet from the BZ mechanism. Okay.
I think we can talk about it.
Okay, all right, okay. Yes, please.
Yeah, so there are some observations indicating that the emission is not so highly collimating as the jet BLANDFORD-ZNAJEK, for example, would suggest. Does your model explain those cases where the possible emission angle is larger than, for example, 10 degrees, semi-angle, or?
Which angle is larger than your viewing angle? You mean, or
jet opening angle?
The jet opening angle.
Yeah. I know there is some cases, just looking at the break of light curves, suggesting that the jet opening angle should be larger than what this mechanism of jet.
Okay. We will get into that a little bit later. For this purposes, I'm not worried about that because we're in a phase where we're looking down the barrel of the jet right now, and we're so the gamma rays are so highly beamed from relativistic beaming. I'm not even worried about the opening angle yet because we're inside of it.
Phase.
Yes.
So you're not looking at that.
That's right. That's right. That's right. Okay. So one last slide, because what is in the back of my mind with all of this is can I connect this and learn something about the progenitor in some way? So I did, the absolute simplest thing that you could ask your students in your classes, in your intro classes to do, and given those fields that we got out, the magnetic fields of 10 to the 15 Gauss or so, what does that imply for the progenitor star of a massive star, for example? So if you pick a massive star, assuming magnetic flux conservation. So if you pick a massive star of 10 to 12 centimeters, you need a magnetic field in your progenitor of around 10 to the 6 Gauss. Okay, and then likewise, you can play a similar game for short gamma ray bursts, and you're getting a few times 10 to the 15 Gauss, which Ferrier will tell us is not so crazy in some cases, thankfully. But again, this is just simple flux conservation. By no means is that necessarily the source of our magnetic field, but it's something that you can play.
Do I understand this now correctly, that there's a 10 orders of magnitude difference in the magnetic field?
Yes, but remember, this is a star that's 10 to the 12 centimeters, and this is a star that's 10 to the 6 centimeters. This is a a compact neutron star of about 1.5 solar masses. This is a 10 plus solar mass star with much, much larger radius. So, yes. Okay, let's zoom out now. So that was focusing on the inner engine, but now let's ask, what can we learn from the environment, from around GRB systems? And I'll remind you that the afterglow is a result of that forward blast wave decelerating in the environment around the central engine. So the afterglow is a reflection of the environment of a GRB. So for long gamma ray bursts, I'm going to focus on the long ones right now. We can talk about short gamma ray burst afterglow if you want. I've looked into that a little, but I want to focus on the long ones. So 95% we see in X-ray afterglow, 70% in the optical. For radio, we only detect 30% of long gamma ray bursts in the radio afterglow. So nobody was too worried about this for a long time. It's just like, they're fading and self-absorption, and who knows why we're not seeing the radio, but it's no big deal. It fits within our nice, pretty picture. But there was a really interesting paper in 2012 by Hancock, Gensler, and Murphy that did some cool image stacking techniques that I don't fully understand, but it seemed to me like they knew what they were doing. And they suggested that there's actually a radio quiet population of GRBs, that there's some GRBs out there that just do not produce a radio afterglow, which I thought was strange, and it doesn't really fit with our understanding. So I wanted to look at that a little closer. So the selection effect game with GRBs is a hard game to play, and I don't know the best way to do it. But what I did was to take the brightest bursts, meaning the isotropic energy is greater than around 10 to the 52 ergs. And I looked at those that were followed up in radio, and I looked at their properties for the ones that had a radio afterglow and the ones that did not. And something that surprised me, at least, came out of this, and that is that the radio bright ones, the ones with the radio afterglow, were longer in their gamma ray duration, in that initial burst, and more energetic than the radio quiet ones. So this is their average redshifts, which is statistically similar, but this what I call T-int is it's corrected for cosmological time dilation, so it's the internal duration of the gamma ray emission. And then this is their isotropic energy. And it's actually probably better if I show you their cumulative distributions. So it turns out, and your favorite statistical tests that you want to do to compare these properties, there's a significant difference in their intrinsic duration and their isotropic energies, but not their redshifts. The redshift range of these populations were the same. So this is suggesting that there's some connection between the inner engine part, which sets that gamma ray duration and the energetics, and the environment, which is reflected by the radio afterglow, the presence or absence of that. Okay, and so I'd like to understand, why that is. Can we use this somehow to make a comment or learn something about their progenitor systems? So let's remind ourselves about the inner engine part. We can have these so-called collapsars, these collapsive massive stars. We can have a range of binary systems. So I know we normally talk about neutron star for short bursts, but let's imagine that long bursts can also result from various binary systems that one can concoct. There are many. Maybe one of the more popular ones is a helium star merger with a compact object. You can get the energy and timescales you need. And then what potential environments do we have? I'm going to oversimplify, of course, but we can get from a wind environment, a wind-like environment, or a more constant external medium that doesn't depend on distance from the central engine. And, as you may know, from massive stars, we expect strong winds, and that will lead to this 1/r² density around the central engine. For binary systems, you can get kind of whatever you want. You can do all kinds of things with binary interactions to get the medium that you want around there. So how do I understand this connection between the radio bright and dark GRBs and the intrinsic inner engine properties? It's really anticlimactic. I don't know. I wish I did. I don't have. There's so many different possibilities that I could construct that it got a little to the point where I threw up my hands and walked away from it for a bit. But I came back, and my feeling is now possibly, and this is ongoing work right now, that I think that actually the radio bright, longer duration, more energetic GRBs might be coming from still a massive star collapse, but one in a binary system, as compared to the shorter duration radio quiet GRBs, I think might be just a single massive star collapse. And we can get into why I think so. Like I said, this is ongoing work, and there's lots of routes to go, so if any of you have any thoughts, I'd love to hear them. Yeah.
So if there's redshift information, probably there's been an identification of a galaxy, a whole galaxy for these gamma bursts. Do the galaxies look the same?
To our knowledge, yes. That's a great question. I looked at offsets. I looked at host galaxy information. There was no other. I looked at every possible property between these two populations that I could, and did not find any difference in those things. And part of it was the numbers are not good enough to do good statistics. So nothing definitively. One thing I can say is that it was only the radio bright population that had GeV emission. Okay, that could matter. That could be significant. Did you?
Mine was a similar question. Was there any other aspect of the afterglow, like X-ray brightness or something that correlates also?
It's a great question, and so at first glance to the level I looked into it in terms of like the just looking at the spectra and the spectral fits, the spectral indices, these kinds of things, I could notice no difference. The flux level, all of that. I looked at the properties that are available, the data that are available in these other wavelengths, and I could not see something. But that said, I did things like peak flux, spectral index. There are probably smarter ways and deeper ways to look at the other the other multi-wavelength info that I haven't thought of yet and haven't done yet. So again, I'm open to any thoughts on that. But at first glance, none of the other observations seem to indicate a disparity. So, yeah.
Could you say why you think that it would be a merger?
So it's not necessarily that it has to be a merger, but that it's in a binary, because that will give it a lot of angular momentum. It could give it a lot of angular momentum, which may allow the duration to be extended, because you may be able to sustain a disk for longer. Okay. And the other,
But how does that explain the absence or the presence of a radio afterglow?
so that's the next part. So in a binary system, you can get a medium around that doesn't look like a wind. I could get more of a constant density like medium, and my radio afterglow lasts longer in that medium. It decays faster in a wind medium. So I think that's the connection. That's, you know, my hand wavy thought at this point that I need to look in a little closer, because I mean, if anyone here is looking at binary star interactions and wants to collaborate on this, come talk to me. I would love to. This is my thought. Okay. Other thoughts, questions? Yes?
How important could metals and dust in general be in the local environment?
Important in terms of, you mean the radio afterglow
Yeah.
itself? Yeah, I mean, I don't know that for the radio that part will matter. I mean, certainly the presence of material will contribute to whether or not you get self-absorption. But the metals and stuff, it's my understanding that will affect your optical spectrum more.
Yeah.
So I'm not sure. That's a good.
If the dust gets heated up and re-emits
Yeah.
light.
But I think that will be at higher wavelengths than what I'm talking about here.
Ah, okay, yeah.
Yeah. Okay. So one last thing about this before I move on to the last part of my talk is that one difference that I noticed between these two populations is that if you look at that intrinsic gamma ray duration as a function of redshift, the radio loud population shows an anti-correlation between those, meaning bursts in the higher redshift universe were shorter duration than in the lower redshift universe. And the radio quiet population, although there were only about 40 data points in there, so take that with a grain of salt, but the radio quiet population did not show that. Okay, and there's maybe about 100 in here. Okay, so we'll come back to this thought, but what this got me going down the road of thinking more about should we be looking at really, let's look at the evolution of these GRB properties like duration over cosmic time and see if that can help us learn something about their progenitors. So again, what can the cosmological evolution of gamma ray burst properties tell us about their progenitors? Okay, so what I have here, this is this isotropic energy, or you can plot it in luminosity here as a function of redshift. And this green line is a flux detector limit. So if I can only detect, say, 10 to the minus 8 ergs per centimeter squared per second, I plot that on my luminosity redshift plane. It makes a truncation in that plane. It's been known for a while. A lot of different studies have suggested that these quantities of energy and luminosity evolve with redshift, with GRBs being brighter in the higher redshift universe. Even when you're doing whatever you can, using all kinds of special techniques, which I can talk to you about if you'd like later, to account for that truncation. So obviously the truncation in the plane produces a correlation, but even accounting for that, you still get a correlation between those variables. Okay. Now, that's nothing new. That's been around for a long time. What is new to my knowledge is that when you actually correct for the beaming angle of the jet, for about 140 bursts, we have an estimate of how beamed the jet is. From the later time afterglow observations, you'll see a break in the light curve when your relativistic beaming reaches the physical opening angle of that gamma ray burst, and you kind of lose photons to the side and see a steepening of the light curve, and this gives you a constraint on how open that jet angle is. Okay, so we have that info for about 140 GRBs. So then you can correct for that in the sense of I'm not taking isotropic energy, but I'm taking actual how much energy is in that jet. And when I do that and I plot it against redshift and account for the truncation, etc., I find there's absolutely no correlation between energy emitted and redshift. So the implication of that is that that beaming angle is anti-correlated with redshift. In order to get isotropic energy correlated with redshift, but energy not correlated with redshift, then you need that the jet beaming angle is narrower at high redshifts than at low redshifts. And indeed, when we plot up the data, that is what we find to like around 5 sigma significance. Okay, so I wanted to, I think this correlation, I've thought a lot about what selection effects could potentially produce it. I think that it could be something that's real. And I would like to know that if it was, why would that happen? Why would you have more narrowly beamed GRBs in the high redshift universe? So that's something that I've been thinking about lately in a lot of different ways. What properties of the progenitor determine your jet opening angle? And so before we get into that, I want you to, I showed you all my pictures before were big cheats in terms of just showing you this jet launched without any junk around, right? But in reality, if we're talking about these long gamma ray bursts and a massive star collapsing, and even in the short gamma ray burst, you're going to have junk through which the jet has to propagate, okay? So this is a simulation from a long time ago, Zhang 2003, showing a jet propagating through a stellar envelope. And the jet needs the jet power needs to be above a certain threshold to make it through that stellar envelope. I show that threshold here by this purple band. In order for that pressure of the stellar envelope to collimate your jet, there are certain conditions for that to happen. That's shown by this mess up here. So I'm not really going to talk much about that because all of the data points need to be less than this for jet collimation to happen, and it happens easily. So this here, these black points are the luminosities, GRB luminosity as a function of jet opening angle. They fall along the band that I've plotted here for the minimum power you need to launch a jet. You may feel worried that some fall below this minimum requirement, but remember what I'm plotting is the gamma ray luminosity, not the jet power. So there's some efficiency factor, and I may have made an assumption of too high of an efficiency. These just may be lower efficiency GRBs. I also had to make assumptions about the stellar envelope here. I may have made the wrong ones. I'm not too concerned that there's a few below. If you want to talk more about that at the end, we can. Anyway, this is just, I start here just to think about, okay, what does it take to punch through a stellar envelope? And then let's do something very simple and think about the pressure balance between the jet pressure and the cocoon pressure, that pressure of the envelope, cocoon system. And if you play this through, you do that just simple pressure balance, you get that the jet opening angle goes as the jet luminosity over this is the average stellar density. Pick your star and it has some average density, radius squared to the 1/2 power. And if you look at massive stars and their average densities, you find that they really are mostly dependent on mass and less so on radius. Okay, and what this leads to is that your average jet opening angle goes as the jet luminosity over the mass of the 1/2. And I highlight the 1/2 power. It's a conservative estimate, and it can be even stronger than this depending on the assumptions you make about that stellar envelope and shocks that may happen to help collimate. Here I made no assumptions on shocks helping collimate, so this is what I view as the more conservative estimate for how jet beaming angle depends on your star. So I'm not in this particular field, and some of you maybe can help me with this, but as I understand it, there are suggestions that the characteristic mass of the IMF evolves as a function of redshift, with that it being higher in the high redshift universe. And if our average stellar density goes as mass, this correlation that we see is consistent with this IMF evolution. So again, higher mass stars have higher average density and are collimating your jets more. So you get more narrowly beamed stars in the higher redshift universe, is the idea here. Any questions about that? Okay. So that's all fine If you can swallow all of those, arguments, that's fine. But what I think I care about more is, what does this imply then about what we think we know about the high redshift star formation rate? As I'm sure many of you know, the star formation rate is a tough nut to crack. It's hard to get a handle on it observationally above a redshift of a few. And GRBs have been, since the first days of discovering their redshifts, been, people shout out about how we can use them to understand the high redshift star formation rate. And it's been hard. There's a lot we don't understand. And this beaming angle evolution throws a little bit of a wrench into it, because what that means is that if GRBs are more narrowly beamed in the high redshift universe, then we're missing more of them, right? Because there's more of them pointed away from us. It has implications for this. So let's take a look at this. This is the star formation rate that I'm going to estimate. This is my observed gamma ray burst rate. This F beam here is going to account for this. So my jet angle evolves as a function of redshift, and so the fraction of burst that I missed due to beaming is going to evolve as a function of redshift. Here's my cosmological volume factor, and then this is the fraction of stars that make GRBs, okay? So this is how I'm relating the observed gamma ray burst rate to the star formation rate. And this is taken from a really series of nice papers by John Beacom and Kistler and Nicole from 2008, 2009, this equation. Okay, but let's plot that. This is the star formation rate on the y-axis, redshift on the x-axis, and I picked different functions for this F beam, where this one up here near this blue line is consistent with what I'm seeing with this beaming angle evolution correlation, this beaming angle redshift correlation. So this may upset you, that then this means that the star this here is the Medow-Dickinson star formation rate, if that speaks to you. It's just sort of a classical functional form of what we think the star formation rate is. But if you take the GRB data and you account for the beaming angle evolution, it says it's star formation in the high redshift universe is much, much higher. This is assuming some constant fraction of stars make GRBs and an arbitrary normalization. So I normalized these curves all here. So don't get too freaked out. Maybe everything needs to be renormalized and brought down a little bit. But anyway, it does imply that the star formation rate is higher than what we expect than if we don't account for beaming angle evolution. I think I'm going to skip that. You can play the game another way if you want. Let me go back to that equation. Oops. I can assume that gamma ray bursts follow the star formation rate, so I can plug in my Medow-Dickinson function for the star formation rate, and then I can solve for this fraction of stars that make GRBs and ask how many, what fraction of stars make GRBs, assuming they follow the star formation rate. And in that case, you get curves like this. Again, accounting for this beaming angle evolution. So the green line is mild. Sorry, I changed up the numbers just a tiny bit, but this is a mild beaming angle evolution. This blue line is consistent with what I'm seeing in the correlation that I showed you between jet angle and redshift. And again, it's what this is saying is that if gamma ray bursts follow the star formation rate, trace the star formation rate, that means that a much higher fraction of stars in the high redshift universe make GRBs than in the low redshift universe. Okay, so what I haven't talked about is other factors that play a role in all of this. In particular, the jet launching mechanism, this BLANDFORD-ZNAJEK effect, should matter for jet collimation, or I would think it does. I would think that if your black hole is spinning faster or your magnetic field geometry is configured in such a way, that will affect your jet collimation. So Valeria Hurtado is working right now on some really nice 3D GRMHD simulations looking at exactly this problem right now. So stay tuned for that. And yeah, we hope to put all of it together to try to understand what is setting the beaming angle of gamma ray bursts and understanding this evolution. And of course, in all of this, we have to consider also relative rates of different systems at different redshifts. Aichi and Eicheltap at Los Alamos is trying to use machine learning techniques right now to look deeper into that problem. But to summarize, so I can leave time for questions. So looking at the inner engine seems, just from luminosity requirements and a BLANDFORD-ZNAJEK jet assumption, it looks like GRBs are magnetically arrested disk systems, and that seems to fit with what we see in their prompt emission observations. There's some interesting suggestions from the radio afterglows of bright or energetic GRBs, and radio dark versus radio bright seem to be different from each other. And the jet opening angle appears to be evolving through cosmic time, and this has some important implications for the high redshift star formation rate. And with that, I will just want to thank some of my collaborators and thank you all for listening.
Hey, I appreciate many of the subtleties in your talk there, and also appreciate your scenario explaining a wide variety of things here. So well done.
Thank you.
Could you go and make some predictions of things not yet tested? Put it down and make some predictions for us.
Okay, so you're gonna hold me to much? Should I put money on this, or?
No, whatever.
I think the biggest one for me would be when we get better estimates of the high redshift star formation rate. I would predict that it's going to be higher than what we think it is. That's where I would go. Other predictions are not really predictions, but I believe that we will see that as we get more data, the jet opening angle redshift correlation, I think that will be bolstered by more statistics. I don't know if that counts as a prediction, but that's another thing I think is real there. Yeah, is that how many predictions do you want?
That's fine.
Okay, thank you. Good. Yes.
Thank you, Nicole, for the talk. I was intrigued with the correlation that you found between, or you showed between the effective Lorentz factor, or the maximum Lorentz factor, and the variability. And there is another system that is not a GRB that almost definitely is a math accretion flow, and we can make those measurements separately. And that's M87. We know everything about the jet. We measure it at very high energy, so like photon energies, we can infer at least a limit on the maximum Lorentz factor, and now we can see with the Event Horizon Telescope the variability at what you would call the central engine.
Yeah.
So is it a direct connection? Can I just take that correlation, multiply by the mass, and get the same number?
Yes,
or is
I'm
it
glad
something
you.
more that you're assuming that is specific to GRBs and not to those materials?
No, I'm so glad you said that, because in fact this correlation is seen in AGN as well. So it scales, and I think that so you can just scale it as you need to. There's nothing that I assumed here. I should stop. No, because our GRB disks are very super Eddington, so there's that. I always forget that AGN aren't necessarily that such. So,
where does it go? Where does that go into the calculation?
So in compute, I guess it's in the modeling of the disk, and that was done by my collaborator Wei-Hu Lei. In that, let me find his. So he calculated an NDAF disk, and the accretion rate there came into it, so that it came in there in terms of the wind that he estimated to baryon load the jet. It came in that part. But the correlation itself between variability in AGN versus the estimates of Lorentz factor is observationally there. It's a good question, though, yeah.
How is radiation pressure factored in these cases? Because if it's highly super Eddington, then we don't have reliable radiation transport schemes.
We're not at that level of detail for doing radiation transport with GRB disks by any means. It's not really, no, it's not. It's my short answer to that. Yeah. Yes.
So long GRBs are associated with broadline 1C
Mhm.
supernovae, and you mentioned earlier that these broadline these long GRBs associated or related with these metal core
Yes.
dwarf galaxies, and that really pointed to the binary stars. It's very hard for a single star to lose its hydrogen and helium envelope in a metal core environment.
Yeah.
Do you see that metal core trend and broadline 1Cs for both your radio loud and radio quiet?
That's a great question. Yes, sadly. I had hoped there would be a disparity there. And there's not good numbers, but I found broadline 1C in both populations. That question is really fascinating to me because I don't know, I don't know the supernova literature super well. But as I understand it, that there's some genericness about a supernova, in quotes, in terms of what we call a supernova associated with a GRB that may not even have spectral lines there, but we see a bump, and we think it at a certain time, and we think that we call it a supernova, but that could be a generic term for outflow. And so in terms of how that plays a role in all of this, and also issues of getting rid of hydrogen and helium in a single star system with hiding it. I don't know how you feel about that. People will sometimes mix and do things, fancy things to hide the hydrogen and the helium. That could be a way. I know some people hate that, and I don't know enough to comment whether that's a viable thing or not. I don't know if there's 1BC people in here that have feelings about that.
Can't hide it.
Can't hide it. Okay, well there you go. Then there you go. So then, then binary systems would be good. And so then, I see then your point being if you see 1BCs with the radio dark, which I think are single stars, right? How do you get rid of your hydrogen helium? Yeah, good question. I don't know. And I would love to go back though to those supernovae because there were only a couple in the radio dark sample, and I would like to see. Are they really supernovae? Like how well established are they? Because like I said, sometimes we'll see a late time bump and it will be called a supernova, and there's not great spectral information there. So, yeah.
I have a question, I guess, about how opacity factors in, because at lower metallicity you have lower opacity and the stars are more compact.
Yes.
So that could give you a smaller opening angle because the average density of the star is higher.
Yes, exactly.
And also the stars rotate faster.
Yes.
So a higher fraction of all stars might
Exactly.
have momentum. Is that not enough?
No, that could be the actual underlying thing. I talked about mass, but really, I mean, relatedly and importantly is the metallicity factor in all of this. And I think maybe that's the bigger thing possibly is that, like you said, low metallicity is more compact, possibly retaining more angular momentum, and maybe that's the reason behind this all. That's a great question. Sorry, I'm like... and I mean, yeah, that's all I'm saying now. Yes, that's an absolute factor in this and could be the reason. So that's why when I plot these plots, I kept it as density and not mass, because there I can talk about, I don't have to say that mass is the factor, and I can talk about the compactness really and factor in that metallicity factor. That's a
So
good point.
even if the IMF stays constant, the average density could be evolving.
Because of low metallicity, exactly.
Or the IMF could be evolving, which is your second argument.
That's right. That's right. So if I just not worry about metallicity and call it constant, then we can do this with IMF evolution. But exactly as you said, the IMF doesn't have to evolve. We can do it with metallicity too.
I don't know if quantitatively it's enough, but it goes
Right.
in the right direction.
So it does go in the right direction, and we have not done the calculations quantitatively, but that's something on our list with all of this. Yeah, that's a good question.
Well, if there are no other questions, let's thank the speaker again.
Thank you so much.